leave that there. Yeah, that'll work. So it won't matter. 63. All right, I guess I've got just 20 seconds. Just a good time for non-class announcements, right? Don't forget, if you're a Wisconsin resident, there's an election on Tuesday, so please get your voice heard there, and please complete the census as well. I noticed when I logged into Canvas this morning, there was some instruction about what happens if you're if you were, prior to the break, living on campus versus off campus. The short version of it is, if you were living on campus, the campus itself is submitting some census data on your behalf, but I think I think they're still clearing up some things. So as there's more info, I will try to share that along. Let's see. I tried to pick a quote from a song that I hope you all know. Just trying to keep the good positive energy going, and of course, well, Bill Withers just passed away last week, so I thought it would be an appropriate song to pick. Let's see, what do we... Oh, yes, a round of announcements, I think. Okay. Exam this Thursday, and this curve sketching handout that I meant to post on Wednesday, I didn't even notice that I didn't get around to it. Just there's been a lot, I think for all of us going on. So I posted that in Canvas. I actually have Canvas open. I'll point out a couple things. Practice exam 3 stuff and the exam 3 info I just posted this morning. I was still figuring out a couple things. For the quiz, a slightly new format. So I ought to just comment, the reason I did quizzes last week the way I did was I didn't want to assume everybody had a smartphone or something to take a picture with. So I thought, I know it was probably a little clunky, but getting people to turn in things that they've typed was meant to try to meet the needs of everyone. But I think what will work out better here is for quizzes here on out, we'll try this. I'm not trying to stick to any one thing. I just want to see if there's going to be something that works, and I think this will be best of both worlds if you just turn in a picture. So that will allow you to write down an answer to a quiz question on paper and then take a picture with a phone if that's what you have. And if not, you can still type and then just take a screenshot. So, nothing's ideal, but I'm trying to, create some flexibility. It'll having the different formats is tricky on my end of Canvas, but I'm just trying to create some flexibility for you. So I hope that'll work out. There is that, just as a reminder, this before an exam, the day before, so on Wednesday, please complete this pre-exam inventory. And then Thursday for the exam itself. So the wording here is a little funky. Sorry, I just noticed. I meant to say you can start the exam anytime after midnight on April 9th. So you have between April 9th and April 10th this 48-hour period. Not that you have all 48 hours to do it. What I'm saying is some people might be busy on Thursday, or want to study a little more, so then you can take the exam on Friday instead. So I'm just recognizing work schedules are different and all kinds of things like that. But at the same time, to minimize any kind of collaboration or anything like this, 5 hours. And not that I want you to spend all 5 hours. It's just like, take 55 minutes to do the exam. That's how long it's supposed to take. If you want to take a little longer, fine. But the point is, don't use up all 5 hours. That's just wasting your own time. Just, take an hour or maybe an hour and a half, complete the exam on paper, and take some pictures of things, and then upload these. And the 5 hours is just meant so that you don't have to rush about that. So just to point out a couple things, because I say these things, but I know that it's a little more helpful if I point them out. So I signed into Canvas. It gives me inside this purple magenta-y color sort of a student view. So I can't sign in as a student, but it lets me kind of simulate this. And if you click in the quizzes area, because of the new format if it will load, come on, there we go. Yeah, so if because of the new format for quiz 13, there's a new practice quiz. So it's in all caps here, new practice quiz. Again, does not count for credit. I would just give that a try. I'm not going to grade it. Once quiz 13, once people have uploaded their answers by the end of the day on Tuesday, I'm just going to delete the new practice quiz thing. So it's just a chance to try this format again, just like if you're going to try the new thing of taking a picture, or you're going to type and then take a screenshot. Just giving you that opportunity. And then sort of in the same spot for Canvas, it's called a quiz, but that's where there's a practice exam here. Again, this is ungraded, so I will just, once the complete exam, Thursday's actual exam is done, which you'll also find in this area, I just haven't made it yet, then I'll just delete this practice format for exam 3. So, I guess I should also explain, let me go to one other area here. Sorry, if you go to the assignments area, we'll let it load, I think, because I'm in a video conference with y'all. This is taking just a little bit longer than normal, but as usual, it was just there. I'll just, actually at the top, I will sort the assignments by type. You can also use the search box. So under exam 3, just like where exam 2 in the same area, there are sort of the traditional links that I have here, compare, contrast, find the error, and a practice exam and key. The practice exam and key are sort of in that paper format. Excuse me. What I just posted this morning is this exam 3 info. So it does the usual things of talking about coverage of the exam, but it also tries to clear up a little bit what I mean by within a 48-hour window, you have 5 hours to complete the exam. So it clarifies by trying to provide a couple examples of this. So please read through that. If anything's confusing, just shoot me an email, and I will try to do my best to clarify as quickly as possible. The other thing that I comment actually in this PDF is, why not just have the whole weekend? I've noticed just from last week, this online process is taking extra time. I'm sure it is for you too, so I recognize that, and that's why I'm trying to create some flexibility. But at the same time, if the exam were available all weekend, then I couldn't start grading it. So I thought a 48-hour time frame, so that if everything has to be turned in by the end of Friday, that gives me a fighting chance to get some of the grading done Saturday and Sunday. And this grading format's going to take longer, but if it were, say, turned in on like Sunday evening, then I know that just how the week has been going, like Monday through Friday, not really anything in terms of grading would get done. So this gives me a chance to try to get as much grading of it done over next weekend, and then okay. Enough talk about all that stuff. Let's do this thing. All right. So I hope that's okay for announcements. That already took 7.5 minutes. I'm sorry about that. Okay, so today we start a new section, and conceptually, I hope it's not all so bad. I'm trying something new, even though I think some extra pictures will help this process. So we have so far looked at local mins and local maxes. I'll give you a moment to just briefly recall what's being said here is that a local max is a point in the graph that is taller than or higher than any of the other points, and then a local min is a point in your graph that, compared to all the nearby points, has the smallest y value. Just with the nearby points, right? It's a place where like a drop of rainwater would collect. The new thing sounds real similar. We're going to look at absolute maxes and absolute mins. So I'll sometimes abbreviate that abs max. The difference is subtle in some sense, is that it's a point in the graph that's higher than all other points. So it's like you might have these tiny little peaks here and there. That's a local max. Now absolute max, that's the peak, right? So maybe you've got a couple different mountaintops. Which mountaintop is higher is sort of the idea. So I've got a picture that I want to show you. I've already clicked on the link so that I've loaded Desmos. But in the picture, you're going to see that there will be 3 local maxes, and one of those local maxes is the absolute max. So let me pull up that picture right now. Okay, so in this picture here, just don't worry about what the actual function like the formula for the function you'll find up here, but not that really matters. I just made a function, and the point is in this function, it looks like the domain is only starting at -1.5-ish. But the point is you've got these 3 local maxes, and because a local max is like where a spot where a helium balloon would get stuck. But of these 3 local maxes, one of these points has the largest y value. It's like the peak of all the peaks. And so that this point that's, unlike the 2 purple points, which are local maxes, this orange point is not only a local max, it is also the absolute maximum, or the global maximum, as it's also sometimes called. Okay, so our goal today is to talk about how do we get these, and most of our work today is kind of, let me say it this way, to outline what we're doing. To explore how we get these things, we're going to go based on the picture. However, you'll notice by the end of class today, drawing the graphs all the time, we saw last week, drawing graphs is tedious. So we're going to use pictures right now for a moment to explore how do we do this. And I don't tune out. Like, I think built into what we're about to do is the recipe. Trying to just memorize the recipe on its own is terrible. It's like a very difficult way to deal with this. The whole point is the pictures we're using. I'm just trying to set the stage. We use the pictures to formulate what the recipe looks like. What does a procedure look like? I think when you look at the pictures, it's very convincing that the procedure we're about to describe is the right procedure. And then once we've described the procedure, if you're convinced that works, then we can apply the procedure without graphing. So the purpose of showing you graphs right now is not that we're going to graph in the second half of class. It's to convince you that the procedure we're looking at is right. I want to just extra clarify what an absolute max or min is, or it's also called a global max or min. So I'm going to give you a moment to write this down after I say it. So given a function y equals f of x, and you're also typically given a closed interval of x values, so a to b, including a and b. The absolute max, or the global max, is to determine which x value in the AB interval gives the largest possible y value. And similarly, the absolute min, or the global min, is to determine which x value in the interval gives the smallest possible y value. So I think this one's important enough to write down the definition. So I'll just stop talking for a moment. Okay, yeah, so I know this all is different, and you could, in principle, watch all the videos later, but I think it's good to still take notes and stay active. Just some comments about this. Let me pull up what I have here in my notes first. So we are going to learn the process about how to get the absolute max and mins. So up above, we just said what they are. Now, how do we get them? Why are we doing this? Well, the big application is what all of next week is really about. So the big application is optimization. We've been talking this up for a while. How do you find the smallest of something or the largest of something? You might want to make pollution as small as possible, or you might want to produce the most number of cookies if you're a cookie factory, or maybe more important to you if your actually business is making the most profit. So that's where all of this stuff is leading towards. The overall procedure relies on derivatives, but the thing to remember about derivative is that it's a slope. I should also comment that part of this new process we're about to learn about finding absolute maxes and mins looks very similar to finding local maxes and mins. So there are some similarities, there are some differences to the procedures. And here's where, when we started the chapter, I wanted to remind you that because we're going to start seeing so many procedures, a new one today, and then in a sense a new one next week, although we're just kind of piecing it all together, the thing to remember, the thing that allows it to be possible to remember the different parts of the procedures is not to really memorize all the procedures step by step. It's really to go, that makes sense because the derivative is a slope. So if you recall that derivative is slope, things go a lot smoother. So here's just to explore, right? So before just presenting the procedure, I want it to make sense. And the big story is to first note that to find absolute max, the story for absolute min, same idea, so just stick to absolute max for a second. To find the absolute max, a good place to look would be local max. So typically for absolute max problems, you're given this interval from A to B, so you'd only, like, I labeled just a generic A and B tick marks on the x-axis, and the point is you would only... if we only looked at the local maxes, that'd be like that point, and then this point, and then that point right there. And these local maxes, as we saw in the Desmos picture with a different function, seem to be good places, good candidates to look for the absolute max. Because after all, in this function, in this picture, the absolute max is right there. Okay, so the comment that's down here, though f may be defined beyond the interval closed a to b, like in this example, it looks like this function keeps going like beyond a and b. So like this part I'm highlighting right now, that's part of the function, but it's not a part of the function we're looking at for the moment. We're only looking for x between a and b because in actual real life situations, x might represent a certain thing, and due to government regulation or due to like union labor laws, I mean all kinds of reasons why x might not be able to be bigger than or smaller than a certain number. So that restriction is meant to simulate something that happens in reality. Here's another picture just to show that, you know, to find absolute maxes, it's a good idea to look at local maxes. So I did thicken one point up here to show that is my representation of the global max, but it happens to be a local max alongside three other points right there, and then that hump, and then finally this hump right there. So there are four local maxes, but one of those, the leftmost local max right up there, happens to be the global max or the absolute max. In the example here, I tried to provide dig into just a little more detail to say that the x coordinate A was just generic in the last picture, and right now I'm actually using the number 4, and the y coordinate B, sorry, the other x coordinate called B, I'm using 6. So in last picture was just A and B, they're just generic. Here I'm using two specific numbers, and then I also, the language here I hope is not so surprising based on things that we've seen with local mins and maxes. So this point right there, that point is the one that matters for us right now. And the y coordinate, or that value, it's the value of the absolute max. So we use language like 5 is the absolute max. And we also, then what about, how do you talk about this x value? Because this absolute max, the x coordinate is -2. So we use language like the absolute max happens at x equals -2. So even if you left off this x equals here, just the use of this word at is trying to indicate x values. So if you just say value, or like here 5 is the absolute, that's y value, and then the use of the word at is trying to indicate x value. So this language is very much like when we looked at local maxes. All right, so overall the just general story is it's good to look, if you're trying to find absolute maxes, it's good to look at local maxes. Okay, that I hope seems convincing so far. The one sticky issue is this closed interval AB. That changes things a little bit, and here's the next picture. So the point now is we're almost done talking about exploring how to find absolute maxes. And the new point I want to make is we need to be just a little careful. And the issue is, while it's a good idea to look at local maxes when trying to find absolute maxes, local maxes aren't the only places to look. If we only looked at local maxes, we're going to have a problem. So let's look at this picture. Let's find those humps first, where the local maxes are. There's one right there. And then there's another local max right... Oh, come on. Mouse. There we go. There's another local max right there. The issue is, if we only look at the two local maxes in this picture, then we're going to have this problem, because between x equals a and x equals b, neither of these 2 points represents the point in the graph that has the largest y value. Yeah, so for x values between a and b, the largest y value is actually here. I mean, it's just slightly higher, but this point on the right, yeah, that point right there, the y coordinate is higher than the y coordinate at that local max, or that local max. So this creates a little bit of a problem. So what do we do? Well, still what we said so far isn't a bad idea. We should look at local maxes. We should look at those points, but that's not the only place to look. We should also just look at the point over here when the x coordinate is b. And for that matter, if we were not going to draw the picture, we should also look at this point there when the x coordinate is a. So we should just basically gather together all of the local maxes, because those are good places to look, but then we should also look at the endpoints. So there's the endpoint when x equals a and the endpoint when x equals b. The issue you'll notice at this point right there, what's going on? How did this happen? Is that the point over there on the right, if you just looked at the slopes of tangent lines, or you looked at the derivative, well, the derivative is 0 at that spot and this spot. So where these two errors are, f prime is equal to 0 at those two humps, right? The slope is 0. The problem with the circled point off to the right is that the slope there isn't 0. It's just that the function, we cut it off right at b, because that's what like the union rules or whatever said that, right? Like there's some restriction in the actual problems we're looking at next week. And that restriction sort of cut off this part of the function over here. It's like that part's not to be looked at, and that's what actually created, in this case, the point with the largest y value. So we just need to basically, the story we said of looking at local maxes is good, we just need to be slightly more careful. So the whole point, the short version of the procedure is to say, to find absolute maxes, yes, check the local maxes, that's good, but then also check the two endpoints, and that's really it. So that's the short version. To spell it out with a little more detail, though, yeah, we're done exploring now. I want to describe for you the complete procedure. This would be a good thing to make sure to have in your notes. By the way, everything new today is not part of the exam Thursday and Friday. But still, this would be good for, the future exam 4. Okay, to find absolute max or min. So the setup is you're given a function and you're also given a closed interval. That's the start, right? That's how the problem starts. So given that information, step one is a technicality. I'm not actually too worried about this issue. I'm just trying to follow the book's steps in order. So first you just check the function is continuous. And for us, we're just going to say that it is and call it a day. Part two, find the critical numbers of f in the open interval from a to b. So whether you include a or b, not too worried actually, but the book does say just check for critical numbers in the open interval ab. So excluding the a and the b. Find critical numbers is for us right now the familiar step of like what x values would you include on the f prime number line. The usual story is it's when you find f prime and set equal to 0. So you get some x values from that process. Now, what do you do with, so that should sound familiar from local maxes. Now, once you have those x values, what do you do with them? Well, we need to get the y values. So in step 3, what you do is you find the actual y values using f. So this, I'm trying to make this comment here. You got to evaluate using f, not with f prime. It's real common for people to want to use f prime because that's the function that they just dealt with. But you use f prime to get your x values. Once you have your x values, we need the actual y values, right? So even in the pictures we looked at, we're talking about like in the graph, which point has the largest y value. So look at the y values at the critical numbers from step 2 and also at the endpoints x equals a and x equals b. So just for all of these, the x values discovered in step 2, all the places where f prime was 0, and then in addition, the 2 extra x values, x equals a and x equals b, just apply the function f, see what y values you get. And then in step 4, all we do is really report on the answers that we have. The largest y value that you see is the absolute max, and the smallest y value you see is the absolute min. So you'll notice that you can do all this without graphing, right? So maybe I'll pause, make sure people had a chance to write down this procedure, right? I think when it comes to definitions or procedures, do that. And also, if you had a question, maybe there's a good place to pause for my talking, allow you to ask if you've got something. Okay, I do want to make sure that the parts of class today are fitting together well. So up until before this slide, we were just talking about exploring, right? And the exploration looked at pictures, right? So to discover how this procedure should work, we looked at graphs. And I think it's important, to remember that story in order to recreate this 4-step procedure is otherwise just a lot to try to just memorize. But I think going through that, revisiting that exploration helps. That said, even though we looked at some sample pictures, some graphs of functions in order to come up with this procedure, to actually apply this procedure, thankfully, you don't have to graph. You noticed last week when we looked at curve sketching on Wednesday and Thursday that the process of graphing is tedious. It's time-consuming. There's a lot of parts to it. A lot of chance for errors. The whole point is to apply this 4-step procedure here. You don't have to graph anything. So I hope that makes sense, right? To discover the procedure, we argued why it should work from graphs. To actually do this procedure on a specific problem, you don't actually need a graph. And then I should just, sorry to re-comment on this, but the most common error is once you get those x values, you're done with f prime. People often want to plug into those x values into f prime. I commented, don't plug into f prime up in step 3. I want to emphasize what we're trying to do, and the picture is meant to help, that we need the largest y value, the actual largest y value in the graph of f, not in f prime. So you got to plug into f, not into f prime. So the rest of class today, what I've got for you are some sample problems, examples, and each time what I want to do is not just do the problem, but once we're done with the problem, I'd like to show you the picture in Desmos. That's not the time to tune out. I think seeing the picture, once we've done the work without doing any pictures, it allows you to like connect the things, go, oh, aha, okay, that's what's going on, right? So here's the full question. I'd like to find the absolute max and absolute min of this provided function f of x equals x cubed minus 6x squared plus 9x minus 1 on the closed interval 0, 5. So you'll notice like earlier in a more generic situation, this was called bracket A comma B bracket. So in our case, the 0 is the A and the 5 is the B. So the idea here is just to, I want to do the procedure and all, but like we better understand what the heck we're doing. So just to make sure we're clear with what's happening is, if we were to graph this function, we're not going to until we're done with the problem. That's the neat part. But if somebody just gave us the graph, then if you graph this thing, by the way, the domain is all reals, right? Because there's no dividing, none of those issues. But you take this graph and then you only zoom in on the part when x is between 0 and 5. Yeah, of course, if you can plug in x equals 6 technically into f over here and get a number, but for some reason that, tied to optimization, tied to the applications we look at next week, maybe there's a restriction that x can only be between 0 and 5. Maybe it's like you're, the owner of a small business, of a restaurant, and this x represents the number of pounds of flour that you need to buy in a week, and so you can't buy a negative amount of flour. That's why 0 is the minimum, or things like that, right? So the point here is, when you only look at x values between 0 and 5, what's the biggest y value? And we could, of course, see this if we just graph this, but graphing a cubic function, generally speaking, unless it's a super nice one, it's not a very pleasant process. So we'll follow our set of procedures, and if you wrote them down, step 1 was to check that the function is continuous. Again, this is the step we're just going to do a little bit of lip service to. I just wanted to keep the step numbers the same as the text. A polynomial happens to be continuous, so we'll just call it a day with that. For step 1, I'm actually, when it comes to exam 4, not exam 3 this Thursday and Friday, but exam 4, I'm really not even all that stressed about whether people write about step 1 or not. The key thing then is the next steps 2, 3, and 4. So the question to put specific language from the generic procedure is, for what x values between 0 and 5 are the critical numbers of f. So kind of usual story, we should find f prime, set it equal to 0. So here's f prime, 3x squared from the power rule minus 12x plus 9, and then the 1 differentiates to 0. So there's f prime, we'll set it equal to 0. Usual story, you can, of course, do things to both sides, but just to kind of fit in the same habit as everything else we've done, factor. I factored out a 3. It's actually only after factoring out a 3 that I noticed more things factor, so that x squared minus 4x plus 3 can factor further as an x minus 3 times an x minus 1. Okay, so having factored f prime as much as possible, now we can set each of the factors equal to 0. By the way, when you do 3 equals 0, you don't get a solution. But x minus 3 equals 0 gives you the solution x equals 3, and x minus 1 equals 0 gives you a solution. So you get these two critical numbers, x equals 1 and x equals 3. Okay, so step 2 was to get the critical numbers. Now step 3, if you go back to the procedure, is to now find the actual y value. I need to emphasize that again. Find the actual y value. The big mistake is to plug into f prime. We don't need any more slopes. We actually, if you plugged in 1 or 3 into f prime, you actually know that the slope is 0, because we set f prime equal to 0 up here. And we ask what x values make that happen. So if you did plug in 1 and 3 into f prime, you should just get the f prime value to be 0. We're not any more interested in we already know the slope. The point is that's a place where the if you were to graph, that's where you have this either a hump or a valley, right? So that's a good place to look for an absolute max or min, because that's where there's a local max or min. But what we need to do now is get the actual y values and compare them to the y values at the endpoints. So step 3, find the actual y values. So this should be at the critical numbers at 1 and at 3, and also at the endpoints. So our endpoints in this example are 0 and 5. So you'll notice here what's being computed is f of 1, f of 3, f of 0, f of 5. No derivatives there. There's a lot of arithmetic shown in sort of that part. And if you didn't copy this all down right now, I would get it. I just wanted to make sure to address for people where did this come from, and it comes from back up here how the function was defined. Just give you a moment to stare at that. Again, in this part over here, there's no computation of f prime. There's all trying to find out, like, even though we have not graphed the function on paper or anything like this, we're just trying to figure out where's the largest y value and where's the smallest y value. Are we doing all right so far? Okay, so the final step is really now just to report on this. So what is the largest y value and what is the smallest y value? Well, looking amongst these 4 circled y values, the largest y value is a 19, right? So to report on this, here's the language. 19 is the absolute max. Or you could say that the absolute max occurs at, again, that word at for the x value, at 5. What about the absolute min? So what's the smallest y value? And you'll notice for the smallest y value, we have a tie. That can happen. So the smallest y value, of course, amongst these y values circled there, are we have a tie for first place of a -1. And so we'll use this language. We'll say that -1 is the absolute minimum. And this absolute minimum occurs at x equals 3 and x equals 0. So now we've completed the question. I'll pause, see how we're doing. Do anybody want to unmute a mic and ask, or type a question too as well? I've got a chat window I can see on the other screen over there. Okay, I'm not seeing a question. I will do the following. This slide shows kind of a lot of work. I wanted to show all the steps. Obviously, that's a good thing to do for the first time we're going through a problem. However, all of the work, I think, is now getting in the way of like the big picture. So the next slide, what I'd like to do is just summarize. So no need to copy down anything on the next slide. Because if you've been taking notes, you should have it on this slide. The next slide, I just want to say, here's what we did, right? We took this function that was given to us and the interval that was given. We asked what was f prime equal to 0, and we found out that happens when x equals 1 or when x equals 3. And then what we did was we found the actual y values. We did this using f, right? Using f, not using f prime. So we plugged in x equals 1, we plugged in x equals 3 from the prior step. We also plugged in x equals 0 and x equals 5. So even here, even in these sub-bullets, I didn't show all the work right now. That was on the previous slide. Sometimes the work gets in the way of the bigger picture. And I did put these comments here that the largest y value was 19, and then we had a tie for the smallest y value. Okay, so that's meant to be a bit of a summary to then just repeating this language. This much is a copy paste, right? That we had 19 was the absolute max, occurs at x equals 5, and -1 was the absolute min, and it occurred twice at x equals 3 and at x equals 0. The most important thing I want to say about this is that we did all this without graphing at all. That's the neat part, right? And that's somehow it's like we're getting a lot of the picture, or at least the things that we need for what we're doing next week with optimization without having to graph. That said, even though we didn't graph, to help really clarify what's going on, I would like to try to point out all of the features that are in the summary here in the graph. So I've got that already pulled up in Desmos. I just need to switch tabs or whatever to over here. Okay, so first of all, I should point out that what you see, if you can also click on the link yourself, either now or later, but if you maybe look at just my demo of it right now, you'll see what I've done is in blue, I have the entire original function, and then in red, I have the restriction of the function just to x values between 0 and 5. Sorry for the curly braces you see kind of off to the left. Maybe I should point out where, like over here. Not that you need to look at all that carefully, but that's just the Desmos notation to restrict. So the whole function is in blue, just the part we need to look at is in red, and that's why I don't know if it shows up clearly enough on your screen. It will, certainly if you click on the link later. That's why you see kind of a blue part, and the thing that looks sort of like a dark magenta, it's actually because it's a mix of the blue and the red. So I'll turn off the red for a moment just to say there's the entire function in blue, but the point right now is we're not supposed to look at all x values just between 0 and 5. So I turned off the one in blue because we're only supposed to look at this part of the function that's in red. I also went ahead and earlier wrote in all the special points. We had, if I just step back here, we had computed f of 1 was 3, and these other ones, I'll just point out f of 1 was 3. Yeah, here it is, this point, right? F of 1 equals 3 means that the point 1 comma 3 is part of the graph. So that was at x equals 1. I'll have you recall we discovered x equals 1 because we took a derivative set equal to 0. And you'll notice right at that point in the picture, you'll notice that's right there that the slope of the tangent line is in fact 0. Remember, the derivative is slope of tangent line. But as far as where's the biggest y value, again, we plugged into the original function. The biggest y value we saw was 19. It's up here. And that occurred when the x-coordinate was 5. And then for the smallest y value, as you see in the picture, there appears to be a tie. It happens to be the y-coordinate is -1. And it happened when x equals 0 and when x equals 3. So I hope the picture that you're seeing here helps clarify what it was that we did. The rest of class, what I got for you is 2 more examples. Okay, so this one's a little more work. So you've got here the function f of x equals x plus 4 over x. The given interval is 1 comma 3. Taking a derivative here, so first of all, we need to report on is f continuous. Of course, this looks a little more dangerous because of the dividing, but the place where there's a problem is when x equals 0, and we've avoided that because we're only looking at the interval from 1 to 3. So this function is continuous, at least in the part of the function that we need to look at. Again, that first step about the continuous, I'm not too worried about it. The key thing here is, though, we should take a derivative and set equal to 0. That's what step 2 is about. Find those critical numbers. This step 2 is the part that looks a lot like the local maxes and mins thing that we've already been doing. So to take a derivative, by the way, you might stare at this function and say, there's a fraction, 4 over x. We have to differentiate that part using the quotient rule. You could, but I think it'll be more convenient to just think of that 4 over x instead as a 4 times x to the negative first. So if you differentiate the x here, you'll get a 1. And then when you differentiate, so take a look at 4x to the negative first. If you do the prime of that, that'll be a 4 times a negative 1 times x to the negative second. So this minus 1 that I have in parentheses accounts for that minus sign. And then I just already rewrote that x to the negative second as an x to the positive second in the denominator. Okay, so we'll do the usual thing of take what we just got for f prime, set it equal to 0. We've got an equation with fractions in it, so I know that my sort of, I have sort of encouraged you to just factor as much as possible in general for these instead of doing things to both sides. But for this one, I think we break that habit and just say, we got an equation with fractions. I think it'll be easier to deal with if we multiply on both sides by a denominator. So multiply both sides by x squared, got to distribute on the left side. You get x squared minus 4 is equal to 0. Now, I should point out, because we did something to both sides, the left side no longer technically represents f prime. But the thing is, we just need to know when f prime is equal to 0. We're not building an entire f prime sign chart right now anyway. So well, you can solve this equation by doing things to both sides, or since it looks nice enough, I thought we'll just stick to the habit of factoring. X plus 2 times x minus 2 equals 0. So you get here, this should have been on the next line. Sorry. You get x equals plus or minus 2. Those are the two x values. So x is positive 2, x is negative 2. Those are the two critical numbers generally. However, we were only supposed to look at x values between 1 and 3. So we discovered this x equals negative 2, but let's call that kind of an accident. Like, we don't need that x value right now. The only relevant x values for this problem are between 1 and 3. So we're going to just chuck it out. We're just going to throw out x equals negative 2. Just because the problem told us to look at x between 1 and 3 only. So the only critical number we care about for this problem is x equals positive 2. Had we been given a different interval, then we would also look at x is negative 2. So the next thing we do is we look at the actual y values. So take this critical number, the only critical number we want, so because we threw out x equals negative 2, it was not in the interval that was provided. So we find f of 2, and then we also need to get the value of f at the endpoints. Again, because we need actual y values. So I just drew this horizontal line. Below this line, we don't look at f prime anymore. F prime was useful to help us see in the function, where does the function level out? Because wherever there's that, either the hump or the valley, that's where there might be a local max or min. So that's a good place to look for a global max or min, or absolute max or min. But now we need the actual y values. Now we're just actually having a little contest with what's the biggest y value, what's the smallest y value. So you can stare at the computation. I should probably talk through these ones a little bit. I plug in back into the original function up here. I plugged in 2, and so you have 2 plus 4 over 2, or 2 plus, what happened here? This does not look right. Geez, this is not good. Let me try this again here. 2 plus 2, right? I screwed up 2 plus 2. Please don't tell on me. That should be 4? Okay. Wow. I'll fix the slides, obviously, next upload. When you plug in x is 3 plus... Oh, that's... Okay, yep, thank you. That is another typo, so I got to fix that too. So the thing is, we got to plug in for x, and this is a slightly bad copy-paste job, so right there, this should be a 3. So, okay. Oh my goodness, I'm sorry about this, folks. So, yeah, we get, with these corrections in place, so f of 2 should be 4. F of 1 is 1 plus 4 over 1. Again, we're just plugging back into this box thingy up there. We should get 1 plus 4 is 5. And then for this last one, thanks for the correction, it should be a 3 plus 4 over 3. Now, 4 over 3 seems like a lot to deal with, but 4 over 3 is 1 1/3. Or in other words, 1 point and then a repeating 3. So 3 plus 1 for the whole number part is the 4. So 4.3 repeating. The y values to compare, sorry, when I reveal the next slide, these will go away. But the y values to look at are 4, 5, and 4.3 repeating. So the largest of these y values is 5. I'll just fix that number here, right? The largest of the y values is 5. And that y value occurred when x equals 1. So the language we're using here is f has absolute max of 5 at 1. Not that you would need to, in a exam 4 or whatever, you don't need to write in the language in parentheses here, but I just wanted to, again, to emphasize what we're doing and clarify and repeat, in a sense, the definition. What's going on here is for x values that are between 1 and 3, the biggest y value happens to be at this endpoint when x equals 1. And what was that biggest y value? It was the y value 5. For the absolute min, oh geez, what happened here now? Oh, because yeah, same error. Okay, so this was me trying to work off of what I had there. So the absolute of the three numbers here, 4, 5, and 4.3 repeating, the smallest of those numbers is 4, right? 4.3 repeating is bigger. So the absolute min is 4, and that occurs when x equals 2. In other words, for the smallest y value, you get that when for x values between 1 and 3, the smallest y value happens to be a 4, and that happens to occur for x values between 1 and 3. That happens to occur when x is equal to 2. Okay, does this work? I'm so sorry about the errors. I would like to take a moment to look at a picture of all this stuff. I should have probably proofread a little more, but it's easy to miss some. Okay, so there was the 4, there was the 3. Let's see these details. There was a 4 there. Let's see these details in the picture. Now the graph that Desmos provides won't have an error. Okay, so here, this is a funky looking function here. So you see the entire function in red, x plus 4 over x. However, we only, instead of looking at the entire function, now look, I think the point is if you look at the entire function, and you don't look at the endpoints at x equals 1 and x equals 3, you're going to miss some details here. If you only looked at what's in red, you're going to get the 0.24. You're also going to get this -2, -4 down here, because that's another place the derivative just visually is 0. The slope of the tangent line is 0. And those are the only x values you're going to get. But the point here, so you would miss the other, the whole point is let's hide the entire function. We're not to look at the entire function right now. Again, due to some restriction in the applied problem we look at next week, not all x values are considered valid. It's just dependent on the word problem. So you'll notice just this part of the picture, and the smallest y value, again, I should have checked here, the smallest y value is 4. That happens when x is 2. The largest y value is not over here where we see that 4.3 repeating. The largest y value is over here, y value of 5 at the endpoint x equals 1. So that, I hope, does a better job somehow than what we had here. I should pause. Are we okay with this? Okay, the way I had structured things, at least if we were going to all be in person, was in a old PDF I had, this was meant for you to try on your own, but I'll just try to, I've got 4.5 minutes, so I'll just try to explain the way through. This one's nicer because, like, unlike the last one that has fractions, this one, so x squared, sorry, negative x squared plus 6x minus 2 on the interval 2 to 5, find absolute max min. So where's the largest and smallest y value? So step 1 is just to mention that the function's continuous. We take a derivative here, negative 2x, to differentiate negative x squared, and then a 6 as the derivative of 6x. Set this equal to 0. I'm going to go ahead and factor out a negative 2. So I have negative 2 times the quantity x minus 3 equals 0. When you set negative 2 equal to 0, no solution. You do get a solution when x equals 3. And also, we should maybe mention that the 3 is inside this interval from 2 to 5, which is an important step we saw from the previous example. Okay, so we take this x value 3. We also take the x values at the endpoints. That is, we look at x equals 2 and x equals 5. And we should plug in those 3 x values, 2, 3, and 5, into f, not into f prime. So I'm trying to use this language to clarify. We plug into f of 3. I didn't show the work this time around. Hope it's accurate. I was copying an old set of notes. Is 7. When you plug in x equals 2 into f, you get the y value 6. And when you plug in x equals 5 into f, you should get the y value is 3. So this process is real nice, I think, finding absolute maxes and mins. It's in many senses kind of nicer than the local maxes and mins business we were looking at. We just report on the largest and the smallest y values. The largest y value is 7, so that's the absolute max. It happens when x is 3. And the smallest y value is 3, so that's the absolute min. This happens when x equals 5. That happens at an endpoint. So I've got one last picture to show, and I'll just remind you just through the announcements. So in red, you see the entire picture. However, we only want to look at the part when x is between 2 and 5. So you see visually here, the max happens to be 7, which occurs when x equals 3. And then the min, the smallest y value, happens over here. The absolute min value is 3, and that happens at 5. Okay, this is the same slide I did at the beginning, but just in case people had joined late, I wanted to remind folks that there's practice exam stuff posted. The quiz on Tuesday, just again, if you joined late, please submit a picture. And if you'd like to type instead, you can type and then create a screenshot using either Windows or Mac. I did post instructions inside the quiz, so you can see that. For the exam Thursday, I need to just clarify, you can start it anywhere from midnight on April 9th to the end of April 10th. So that's in this 48-hour window. It's not that you have 48 hours to do it. You get a 5-hour. So within that 48-hour window, just trying to recognize people have different schedules now. As soon as you hit start, then you have 5 hours to complete the exam. Even the 5 hours, I'm not asking you to spend all 5 hours doing the exam. It should be an hour, or if you want to give yourself a little more time, no big deal, hour and a half, do the exam, and then upload the pictures for your answers. I think, yeah, that's what I have. Tomorrow, the difference, what we're doing is, we will review this, but I think the key story tomorrow, just to preview this, is there's a lot of things between absolute maxes and local maxes, how to find them, where the procedures are similar. So tomorrow's goal is to really carefully sort out how are they similar, how are they different, and how do we recall all this stuff. All right, see you tomorrow.